We have seen that the change in position of an object with time can be represented on the distance time graph. When we say change in position, we actually mean distance. Now, in simple words, we can say that the distance of an object with time can be represented on the distance time graph. So, if we change in position, if we just change in position means distance, right? And the change in speed in particular direction means variation in velocity. So we can say that change in position is equal to distance and change in speed in particular direction means variation in velocity. So from this we can say that the variation in velocity with time for an object moving in a straight line can be represented by a velocity time graph. And we know that variation in velocity means change in speed in particular direction. So today we are going to talk about velocity time graph. So the variation in velocity with time for an object moving in a straight line is represented by a velocity time graph. In this graph also, time is represented on x-axis and velocity is represented along the y-axis. Now, let's see what kind of velocity time graph we get under different conditions. So, the first condition is when the object is performing uniform motion. So, look at this graph. Here, x-axis shows time and y-axis shows velocity in kilometer per hour. If you can see here, at any given point of time, the velocity remains the same. That is 40 km per hour. So, whatever the time may be, the time is changing, but the velocity is not changing. It is remaining the same. That is 40 km per hour. So, here the height of the velocity time graph will not change with time. Look at this height. It's same everywhere. Okay? Irrespective of the time, it's not changing. Now, the line showing this velocity will be parallel to x-axis. So, this line is parallel to x-axis. From this, we can say that the object is performing uniform motion. Now, from the same graph, we can also find out the distance moved by the object in time. So, we know that velocity is equal to displacement upon time. Now, how can we find out the displacement from this? See, from this we can say that the product of velocity and time give displacement by just changing the side of the time. So, we can get velocity into time is equal to displacement. Now, look at this graph. The region which is highlighted here is ABDC. This you can see, this is a rectangle. Now, here the velocity is AC, that is 40 km per hour, and time is CD. The length of CD is equal to T2 minus T1. Now, if we plug in this value in displacement formula, we get AC is the length of the AC, here is the breadth of the rectangle, and CD is the length of the rectangle. And we know that the area of the rectangle is L into B. So here displacement is nothing but the area of the rectangle. So displacement is AC into CD, because displacement is equal to velocity into time. AC is actually the velocity and CD is time. AC being the length of the rectangle and CD being the breadth of the rectangle, we can say that this is actually area of the rectangle ABDC. So from this we can say that displacement here is nothing but the area of the rectangle ABDC. And we know that AC is 40 km per hour and CD is the difference of T2 and T1. This is how we can find out the distance moved, distance is S, that is moved by the object in given time. In our next sessions, we will talk about how velocity time graphs can show uniformly accelerated motion, uniform retarded motion, non-uniform motion, and even distance traveled.